Welcome back to the Decentralized Application Development Crashcasts. I'm Sheila, and I'm here with Victor. Before we dive in, I'd like to remind our listeners to rate our podcast on whatever platform you're listening to us. Your feedback helps us improve and reach more developers like you.
Absolutely, Sheila. We're always excited to hear from our listeners. Today we're continuing our journey through Chapter 3 of Season 1, where we're exploring distributed hash tables, or DHTs. In our last episode, we covered the concept and purpose of DHTs. Now we're going to dive into the basic operations that make DHTs tick.
That's right, Victor. But before we get into the nitty-gritty, I've got a quiz question for our listeners. Here it goes. Which popular peer-to-peer file-sharing protocol uses DHTs for decentralized tracking of which peers have what files?
Ooh, that's a great question, Sheila. It really highlights the practical applications of DHTs in the real world. I think our listeners might need to think back to some file-sharing systems they've heard of or used in the past. Without giving away the answer, I'd say this protocol revolutionized how people shared files online, especially large files like videos or software.
Excellent point, Victor. Now, let's start by breaking down the key terms for our listeners. We're talking about basic operations in DHTs today, specifically the put and get operations. Can you give us a high-level overview of what these mean?
Certainly. In the context of DHTs, put and get are the fundamental operations that allow the system to function. Put is used to store data in the DHT, while get is used to retrieve that data. It's similar to how you might put a book on a shelf in a library and then later get it back when you need it.
That's a helpful analogy, Victor. So, if I understand correctly, when we put something into a DHT, we're essentially storing a piece of information that we can later retrieve using the get operation. But how does the DHT know where to store the data and how to find it later?
Great question, Sheila. This is where the hash part of distributed hash table comes into play. When you want to store data, you first need a key. This key is then hashed, which means it's put through a mathematical function that generates a fixed-size string of characters. This hash determines which node in the network is responsible for storing that data.
I see. So, if I'm understanding correctly, when we perform a put operation, we're not just randomly storing data somewhere in the network. The hashed key determines its location. Is that right?
Exactly. And the same process happens when you want to retrieve data using the get operation. You provide the key, it gets hashed, and the system knows which node to ask for the data.
That's fascinating, Victor. But I'm curious about potential challenges. What happens if the node responsible for a particular piece of data goes offline?
That's where things get really interesting, Sheila. DHTs are designed with fault tolerance in mind. Typically, data is replicated across multiple nodes. So if one node goes offline, you can still retrieve the data from another node. This replication strategy is crucial for maintaining the reliability and availability of data in a decentralized system.
That makes sense. It's like having multiple copies of a book in different libraries, right? If one library is closed, you can still get the book from another.
That's a perfect analogy, Sheila. And it highlights one of the key strengths of DHTs, their resilience. Now let's dive a bit deeper into the put operation. When you put data into a DHT, you're essentially creating a key-value pair. The key is what you use to retrieve the data later, and the value is the actual data you're storing.
I see. So, if I wanted to store my favorite recipe in a DHT, the key might be Sheila's famous lasagna, and the value would be the actual recipe text?
That's a great example, Sheila. However, in practice, keys are often hashed for uniformity and to ensure even distribution across the network. So your key might end up looking more like A1B2C3D4 after hashing. This hashed key is what determines which node or nodes will store your lasagna recipe.
Interesting. So when I want to retrieve my recipe later using the get operation, I'd need to know that hashed key, right? How does that process work?
Exactly right, Sheila. When you perform a get operation, you provide the key, or its hash, and the DHT system uses that to locate the node responsible for that data. It's a bit like a treasure hunt, where the hash is your map leading to the treasure, in this case, your delicious lasagna recipe.
That's a fun way to think about it, Victor. Now, I'm wondering about potential challenges. What if two pieces of data end up with the same hashed key? Is that possible?
Great question, Sheila. That scenario is called a hash collision, and while it's rare with good hash functions, it can happen. DHT implementations need to have strategies to handle these collisions. One common approach is to use a technique called chaining, where multiple values can be stored for the same key, forming a linked list.
Fascinating. It seems like there's a lot of complexity behind these seemingly simple put and get operations. Are there any best practices or tips for developers working with DHTs?
Absolutely, Sheila. One key best practice is to choose appropriate keys for your data. Keys should be unique and meaningful. Another tip is to consider the size of the data you're storing. Large data items might need to be broken down or stored externally with only a reference in the DHT. Also, always plan for fault tolerance and consider how often your data might need to be replicated or updated.
Those are great tips, Victor. Before we wrap up, do you have any interesting facts or anecdotes about DHTs and their basic operations?
Sure thing, Sheila. Here's a fun fact. The concept of DHTs was inspired by earlier peer-to-peer systems like Freenet and GNU. But DHTs really took off in the early 2000s with the introduction of systems like Cord and Kademlia. These systems showed how DHTs could provide efficient, scalable, and robust distributed data storage and retrieval.
That's really interesting, Victor. It's amazing to see how these concepts have evolved over time. Now, I think it's time to reveal the answer to our quiz question. The popular peer-to-peer file-sharing protocol that uses DHTs for decentralized tracking of which peers have what files is BitTorrent.
Exactly right, Sheila. BitTorrent's use of DHTs is a great real-world example of how these systems can be applied to create robust, decentralized networks.
To summarize today's episode, we've learned about the basic operations in DHTs, put and get. We've seen how these operations use hashing to store and retrieve data across a distributed network. We've also discussed challenges like node failures and hash collisions, and how DHTs are designed to handle these issues.
That's a great summary, Sheila. Remember, listeners, DHTs are a fundamental building block in many decentralized systems, and understanding these basic operations is crucial for anyone looking to work with or build such systems.
Absolutely, Victor. And to our listeners, we hope you found this episode informative and engaging. If you did, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create better content for you. Until next time, happy coding.